Okay, Bismillah ar-Rahman ar-Rahim. This is the continuation of the lectures on what? Superscalar or parallel architectures, okay? So when I say parallel architectures, we have seen a lot of things in it, and on one side we have what? Functional parallelism. In the functional parallelism, what we gonna have is basically what? Instruction level parallelism. And in this we have basically what? Pipelining, we discussed that. Then volume and superscalar. So we are here, and in the data dependency we have a lot more things and all that we have discussed that. But the thing is that we are here in the instructional level parallelism. There is pipelining and volume and superscalar. We're basically taking up this part first, okay? And we discussed the pipelining. What it did in the basic idea of pipelining is what? To divide your execution unit into many stages because of its functional units, okay? Then undergo the overlapping of the instructions so that one functional unit will be used by particular instruction, then second function will be another, and so on. Depending upon the stages, we have the pipeline. You can have a deeper stage and all that. Lots of things we discussed about the pipeline. And then was the volume. Very large instruction word, which basically does what? Yes? What is happening in the volume?
Multiple execution units execute multiple instructions.
We need to have multiple execution units. Then how we do the instruction, how we give the instructions to the EU, and who will be responsible for all this decoding, etc.
Compiler.
It's a compiler. Yes, is it? In the value we have a compiler, basically, which deals with all this, right? In the instructional parallelism we have the value, and it is the compiler. That's why we said it's a static scheduling, right? While in scalar, superscalar, in fact, not scalar, superscalar, we have what? We have dynamic scheduling. Means how you issue the instructions. Who is responsible for decoding and etc. Here we have the compiler. You have instructions which come to the compiler, and it's a very intelligent compiler who basically does what? Why we need that? What should compiler do? Basic thing.
Dependency free.
It makes your dependency free. It checks the dependencies. We have basically, broadly speaking, two kinds of dependencies: true and false. And true is which one? Raw. And false is like wave and besides that we have also what? Control dependencies. We have control dependencies, is it? And resource dependencies. Now it's the compiler who's gonna check all these things. Hey, what kind of dependencies you have? Everything is gonna be checked by what? Compiler. It is the compiler who makes, who makes a very large instruction word. Basically, which comes out from this compiler is a very large instruction word. In this, we have actually a lot of fields, and each field for every execution unit. Is it? Execution unit. Every field for every execution unit, with having two read ports and one write port. And you can increase many EUs, no problem. And we may have the simple register or the common register. Then register file. Does it make sense what we are doing? Yeah. But in case of your superscalar, we saw that hey, we're not gonna make this as a one instruction, as a one big. Basically, in a value, we have one big instruction. In this, we have packed everything. We have packed instruction of everyone. And what we have done basically is we know this instruction, they have, for example, a dependency between the two in terms of something. So I have to stall actually. I can't use this instruction parallel. For example, this instruction is using some register and this instruction is also using same register. I can't execute them simultaneously. I have to give a wait for this, for example, for this instruction. Let this instruction first do that. But the thing is that the compiler is intelligent. He knows that, hey, if I made him watch, but I'm not going to use waste this slot. Maybe I use another one which doesn't have a dependency. They call it bubbles. So this compiler fills the bubbles. The compiler fills the bubbles, okay, so that, and reschedules them, so that what? Yeah, so that the dependency is mitigated. There may be control dependency also. Okay, how you do by control dependency? Basically, that's a branch prediction, is it? And you may have the false dependency. How you remove the false dependencies?
Register renaming.
Register renaming. Register renaming. Very good. Is it? Because true dependency you can't. You have to wait. For that you have to reschedule your instructions, because you can't execute these two. If it's output, if it's whatever it's writing to, that is to be that's what's called a raw, read after write. What it is, first instruction it is reading something, and then this instruction want to write that. But if it's not finished here, R1 is not finished here. If R1 is being produced here, add R1 to the R2. R1 is produced here, and I'm using this R1 here in the multiplication operation. I'm using this R1 now. I'm saying R3 equals R1 comma R5, whatever. Now, unless I don't have the R1, how can I multiply R5? This can give me the problems. We have done a lot of things. Like we have the control dependencies. In control dependency, for example, there is an if something, then do this, right? Else do this. Now, if we do these instructions in parallel, okay? Unless I don't know, hey, what is the truth value of this if statement? Should I do this instruction or should I go on an else part? I don't know. So, but if I do in a parallel, I will be in a mess. Okay? Maybe I'm doing this and this simultaneously, but the truth value says I shouldn't be doing this. I should be doing something else. So that's why we have to do branch predictions. So speculative branch prediction. It's called speculative branch prediction will help us in that. Otherwise, in parallel, we can't execute them because I don't know exactly what should be the flow of my program. It depends only on the truth case. Okay? So I have to simulate my things and do a branch prediction, and that branch prediction is itself a big chapter, and then I can do these instructions. You getting me? And compiler basically is doing all these things. It's trying its hard, okay? But there are some drawbacks, we said that. The drawbacks are like what? The compiler should be seeing all kind of registers, all kind of instructional architecture and everything. So that means this compiler is fully dependent on this this machine and this compiler are coupled together. That means if you have family of processors, then we can't. Okay? If you have family processors, for every different family member, we need to have a different compiler. That's the problem. That's the problem. And a lot more things we have discussed that in the previous lecture. Now in superscalar, what we have? Yeah. We don't have this thing. We have basically, we fetch instructions and there is now what? Decoder. A decoder is a guy in upfront, okay, which does all the things, and then basically we have a lot of instructions coming up and giving to the lot of EUs now, different instruction of different EUs, and it is the job of actually the and so on. Maybe there will be other guys in between. It is the job of whom? It's the job of the processor. Decoder is the part of the processor basically to see all these dependencies and how this instruction execution happens. Now there is a lot of things to do because we have a lot of instructions going on together, and there may be a lot of instructions are coming, and a lot of instructions are being executed right now. So right now instructions are being executed, not one, many instructions, because superscalar is meant to go for multiple instructions per cycle. This is the basic funda of the superscalar architecture, which goes for multiple instructions per cycle. Okay, so it doesn't have to care about only the mean instruction versus the instruction being executed, the instruction coming with the instruction being right now executed. maybe it's using something and this also needs something, so it can cause a problem. But it also has to take care about the between the instructions. The instructions are coming up, 3-4 instructions are coming up, maybe, okay? There may be dependence between these two instructions itself. And there may be the dependence between these set of instructions and the instructions being executed right now by these EUs. So it's really a complex issue. Okay? So a superscaler basically does what? Basic idea is have a lot of instructions come together, and the decoder is the guy who chucks all kind of these things. That means decoder need to be very efficient. It need to be have all kind of things. Okay? You getting me? So basically, then what is the job of the basically we should see what kind of how superscaler came into being. Basically the IBM. It was basically the IBM where it got the birth. IBM was the pioneer in developing IBM. Any kind of like technology dependent things, okay, the evolution of technology dependent things, we have basically three things. It happens in three things. Like your SDLC, whatever, how you do that, how you make your software even, how you make any machine, how you design. It's about the risk also. How you design? We just have an idea in mind, then we make some sort of design or prototype, something like that, and then on that design we actually make it. So similarly to superscaler, we got three things. Number one is you perceive that you have an idea in mind. You perceive, you conceive basically a perception of an idea that we need to have this much of things, where the instruction will come up, the multiple EUs will do all these things and all that stuff. And second thing is you have some research projects, okay, or prototypes. The people come up, they give you the research projects. Hey, let us have these things. It have this thing, it have that thing, and all that, right? And a prototype will come up. And after that, when prototype and all discussions and these research projects and all pros and cons are discussed, and if there is any, it will be attacker like thing, and when it survives, it gets into the commercial market. You getting me? So the idea was conceived in like 1980s. In 1980 it started, the story. In fact, in the IBM, and there were in 1982, I guess in 1982 it was the Cheetah research project, not a commercial product. It was a research project from the IBM of a first superscalar processor, superscalar processor design. Prototype of that, it's a research project. Then it became the America project. They come up with the America project. Home, IBM, right? And later on, they make actually the same thing, America project, but they name it Power. They need Power 1 or something. Okay, but Power 1 is nothing but America project. This was around in 1982. Then this was starting from 1985 to 87. It was in 1990s and so on. And in these also, when another player called DEC. This was from the IBM. This was the DEC. You can watch it on this. We have here perhaps this thing on our laptops. I saw it here. This is William. This is superscalar introduction. Okay. Was this thing I was on? Yeah. This is Cheetah project in 1982, as you could see here, 1982, right, on the downside. Then from 1985, basically the America project, okay, and it was later on called as, it's not given here, but it's called as what? Yeah, what's the America project called? Okay, and another player is the DEC, which was in 1985 on this time, again it's an America project. They had their, basically they had a Titan project here, they had a project called Titan, which is a superscalar risk-based machine, risk-based architecture, Okay, it was Titan, and they called it the multi-Titan then. Multi-Titan. Okay, as you could see that multi-Titan project. And then another players like Stanford, and also the Kyushu. This was from Japan. University and Stanford University. Stanford University had got two. Which one? March and Torch. Okay, Match and Torch. And in Kyushu, got a SIMP and DSMS. So we got a March and Torch, and here we got what? That's a match, MATCH. And then SIMP and whatever. This is from Japan. Okay, the simultaneously they worked on each on this particular issues. Okay, so this was about the history, and then in basically in 1990s we got the first commercial. This was all projects, research projects. They were all. I told you first the conception was perceived, the idea was perceived, then you conceive an idea, then make a prototype, and then make a commercial project. Then there are a lot of things, these projects came up, and one of them, the first one was I guess from the Intel. Okay, it was from Intel, I guess. Yeah, what was the name of that? I forgot. Has this given?
960C.
Yeah, 560. What's that?
960.
960CA. This is the first our commercial product, and so on. The history. Look at the book and these slides. So do remember all these things, okay? Now this is important. As you can see here, the superscale processing can be broken down into a number of specific tasks. This is what we have to read about, and this is what this is all about. Okay? So with the specific task of superscalar. Okay, processing. Superscalar processing. What is the first thing? Yeah. So we need to do a parallel decoding. This is important because main thing is decoder. We'll discuss that. Let us write first parallel decoding. Number next.
Superscalar instruction issue.
Yeah. This is universal syllabus and all that instruction issue. Then parallel instruction execution. And basically it's about the preservation then. Preservation of the sequential consistency and preservation of the sequential consistency of exception processing. So the preservation of and last one is preservation of consistency of exception. And all that exception handling. Exception processing. Exception processing. Okay. We're running out of time, come quick to this. What we are saying basically is, we say parallel decoding. The first thing is parallel decoding, right? Now we say we have to do parallel decoding. Now because the basic thing in our this what? Superscalar is the decoder. This is the heart of your superscalar. Do you remember the heart thing? Last year? Okay. Second year, yeah. Decoder. This is the heart of your superscalar because decoder is everything. It chucks everything. It has check dependency and all that, right? Now, how will it do all that? Because if it starts doing, because what happens is, depending on this, its decoding is the performance. If the instruction coming, it has to chuck all things, that means it has to wait. The things have to wait. Executions have to wait when the things are being done by the decoder. And it's really a complicated issue, how the decoder works. Because decoding does what? How we do decoding? What's the decoding in it? What do you think decoder is doing?
First check instructions for dependency.
Dependency hacking. What kind of dependency we can have? What kind of dependency we can have?
Data dependency, control dependency.
Resource dependency. Is it? We can have all these things. So how will this mitigate this problem? ये instruction generate करता है actually. ये instructions it generates the instruction to be given to the EUs. Okay? So it will generate an instruction in such a manner जो यानी कि जिसका ये बैच बनाएगा इंस्ट्रक्शंस का, इसके पास इंस्ट्रक्शंस 50 है. अब मान लीजिए 10 इंस्ट्रक्शंस हमारा सुपर स्केलर करता है एक साथ एक साइकिल में. In one cycle 10 instructions. Now the thing is that you get the instructions, you batch the 10 instructions because you have 50 or 100 instructions for example. Now out of these 100 it will batch only those 10 which doesn't have all these things, all these flaws. Then make another batch, then make another batch, then make another batch, and so on. You getting me? So decoder does all this, but we said, hey, why not fasten it? I mean, why not make it fast? Not faster. Why not make it fast? Okay. So how we make it fast? We say, hey, before you decode, do pre-decoding. Do what?
Pre-decoding.
At the time of load. At the
Time of load.
when you're loading, because basically what we have in our architecture is we don't have a cache as a level 1, we have level 2 as well, level 3 as well. We have on-chip cache, which is meant for instructions, called an instruction cache. We may have caches outside our chip. Okay, these days processors, it's this much of processor and whole thing is like a cache. The things are like that, right? Getting me? And when we are loading our instruction into the instruction cache, basically this decoder will work after your instruction cache. When the instructions are in the instruction cache, you give to the decoder. But we say, hey, when we are loading it, right? It's like we are doing something on processing. वो हम लोगों को पहले ला रहे हैं यहाँ पर, उसके बाद हम पूछ रहे हैं चलो क्या आपका क्या नाम है, आपका क्या नाम है, और all that. फिर हम इसके हिसाब से स्केड्यूलिंग करते हैं, फिर हम आपको आगे भेजेंगे. अब हम सोचते हैं कि हम इस वक्त ना करें जब आप चढ़ रहे हो सीढ़ियों को यहाँ तक आने के लिए. You are coming on upstairs. While you come upstairs, I will start asking you, hey, what's your name, what are you doing, and all that, and see the dependency and all that. You are here. When you are here, we've already done the task. It will become speedy. It will make us speedy. It's called pre-decoding. So what I do is, we said, hey, before you have the other level cache, then you go to the instruction cache. You are loading to the instruction cache. This may be level 2 cache, level 3 cache, or sometimes maybe memory. Even if you don't have an instruction cache, other caches, other level of caches. Because these days we have a lot of cache levels, right? So this may be the other level cache, or this may be memory, whatever. But usually this may be the other level cache, like L2 or L3. You're getting things from this cache into the instruction cache. You have a unit in between, pre-decoding unit. You have what?
Pre-decoding unit.
Before you give this to the decoder, the main decoder, right? Before you give this to the main decoder, you have pre-decoding unit. And this pre-decoding unit is doing a lot of things for us. What should it do? What do you think it should do? Number 1, it will categorize your instructions. It will categorize. It will say, hey, what kind of instruction is this? Is this like we input bound instructions, output bound instructions? We have like operation bound instructions, competition bound instructions, floating point instructions. Is it a fixed point instruction? Okay. So we will see what kind of instruction class this is. Instruction class. It will categorize by instruction class. It knows that this is gonna be my load store instruction. So we know if it's a load store instructions, we know we are gonna be having more our resources like registers where from we get the things. If it is like competition instruction, we know, hey, the adders or multiplication, what kind of instruction? Is it multiple instruction? Is it adder instruction? So we will be knowing in advance that this is gonna have my resource like multiplier. You getting me? It will also try to see what kind of dependencies are there in between. What kind of resources are you using? It will list out this instruction needs this much of resources maybe. Okay? So when it's coming up here, I already know what kind of resources you need, what kind of resource this instruction need, what kind of instruction that instruction need. You getting me? So decoder already has something done now. He knows. He doesn't have to see कि कौन सी instruction को क्या चाहिए. He already knows it. The information is prefixed. That means if you have here some sort of like 128 bits, here we have 148 bits because we have appended the information with each instruction. That means we may have that means a resource, more internal memory space. That's not a big issue these days. But if it can speed up my performance, that's big thing. Does it make sense what I'm saying? Okay. So number third is like, we know we don't have only the dependencies in kind of what? Dependencies in terms of difference in terms of data dependencies and all that, but we may have the control dependency. Like I said, you have to execute an condition, if condition for example, and on that condition you want to go where do you want to go? Is it? You have a jump instruction, there's a branch, but if we do execute this instruction which is asking for the condition and other instruction parallel, so that will be waste. Because if this condition is false, I have to go here, not here. That means this instruction is executing in parallel, that's waste. You don't have to do that. So branch predictions. Maybe what my pre-decoding unit will do is it will see the addresses where it has to go. Okay? Like we have function calls. Okay, like we have function calls. Like function, I have to jump it somewhere here. I don't have to do after this function statement, like function call. It says add. After that there may be instructions, but after add I have to go here, where this function is being defined. So calculate that address. If not the physical address, maybe the logically you tell us, hey, where it lands. Okay? So that will give us a lot of comforts here when we're gonna decoding. So we said like what? Address calculation. So address calculations are being done. Does it make sense what I'm saying? So this is all being done by the pre-decoder unit. Now when the pre-decoder unit it does all the job of this. Now decoder is happy. When the things are in instruction cache, we have the added information with each instruction. Because we can't hold that information in pre-decoder unit itself, we have to add that information with every instruction. Now instruction is like calling, hey, I'm like this, because now decoder will chuck that extra information to see what kind of instruction this is. That means to make a batch out of them is easy now. Okay? Because if I want to make a batch out of you, I have to first see you, what kind you are, what kind of resources you want, what kind of instruction you are. Then after that I can make a batch. But now I'm free. I have to only make a batch. Why? Because that job is being done by the pre-decoder unit. It has all done. That's being appended with your each instruction. I have to only open up your box and see, hey, what kind you are. Okay, I'll jot it down. Okay, you are like this. Then I know this and this can be executed simultaneously. They have independence and so on. And I can combine this, and make a batch out of it and throw it to the execution units. Then throw into what? Because the decoder will throw in the instructions to the EUs. Clear or not clear? Sure. So this is your basically parallel decoding. Because you are decoding parallel. Not only you have to here see the dependence of each other, but also to the which is being executed. So a really complex issue. And the next important thing is instruction issue. This is important because after we have been doing all this, what we have to do, what the decoder has to do, it has to do an instruction issue. Is it? After all this stuff, what the pre-decoding and decoder what is being doing, what we have to do? We have to issue the instruction. Now to issue the instruction, we have two issues. We have what? One is called issue policy and issue date. Issue policy will tell us, you can say like this, here. You can check on this with slides also. There is these slides have all this information, right? This is nice. They're nice slides, but they are from the book. So, okay, issue. We got two things. What is that? One is the issue policy, and we got what?
Issue date.
Issue date. Issue policy will tell us basically how you remove the dependencies, like how you remove the false dependency, how you remove the because true dependencies you can't remove them. Can you remove true dependency? There's no alternative but to stall. Like we did a pipeline, we stalled. We have to wait. We have to block. What can we do here? We can block. I will not call it here stalling because that's the pipelining term, because we stall to that step. Okay? You understand that? When we stall, what do we do? We wait that cycle only, for that step only, right? But here what we do is we block this instruction. We say, hey man, you can't do because you have the dependency. Wait for a while, go after that. When this guy has finished writing to a particular thing, okay, or reading from a particular thing, whatever, then you can do whatever. If this is a raw dependence, what I'm saying, if it's a raw dependence, we can block that. That means we can fix that. We can fix that only by waiting, right? But if he has a false dependence, we can remove those. If there is the control dependence, we can remove that. Okay? So this issue policy basically is telling us, hey, how are you going to remove this dependency? And issue rate will tell us how many instructions are we gonna issue per cycle. Because I said superscalar is basically on what? The basic principle. Multiple instructions per cycle, right? But what's the rate of that? What's the rate of that? I mean how many instructions are you being issued per cycle is the issue rate. And issue policy, yeah, what does the issue policy does?
How to remove dependence.
Exactly. You can see this from the slide. If you have higher issue rates, can unduly lengthen the decoding cycle. Now decoding cycle will be increased because if you have higher issue rate, decoding cycle will be because what happens? Because in decoding, if we don't have pre-decoding, I'm saying, if we don't have pre-decoding, then we have to see all those things and dependencies and all that, and I have to also generate many instructions because my issue rate is higher. So that means decoding cycle will be longer. It may take 2 or 3 pipelining cycles, multiple pipelining cycles, because decoding inside I will do pipelining. In the decoder itself is doing pipelining. It will be checking all the dependency. How? By pipelining. Inside a decoder we will be doing these things by pipelining only. You getting me? What basically we have is, I forgot to say, that we have the buffer there. We have the what? Buffer there. Okay? And like we had instruction, this is our instruction cache. Then we may have the buffer out here when we have the instructions, and then we give the decoder. Okay, we may have the buffers to take up a lot of instructions. So what I'm saying is basically, if we have this thing, so we need to have a decoding cycle is longer. So how do we mitigate that? By using pre-decoding. Is it? Because pre-decoding में क्या होता है? पहले ही वो करता है? या कब? Load time.
Load time.
From the maybe L2 cache to instruction cache when it comes. So higher issue rate is good. This is quite obvious. If you have higher issue rate, we have higher performance and all that, but the higher issue rate should not be like that. They are having problems. They should be independent. Okay, independence should be within them. But if there is a more dependence, then what? You can't go for higher issue rate, as simple as it is, because if the dependency is high. So this is quite simple, right? This is understandable. So that's why we have the intricate issue policy. We have intricate what?
Issue policy.
To mitigate all this problem, to tell us how we basically remove these dependencies. Therein we come we have branch predictions, we have shelving, we have the dispatch rates, we have a lot of things. Okay? These are only what are these shelving, etc. These are the issue policies. The issue. What is issue policy basically?
How to remove
Yeah.
dependence.
You getting this? So we have advanced techniques like register renaming. So Shaista, you tell me, where are we gonna remove have register renaming? In what?
Resource dependence.
Always.
Register.
Huh? Resource dependence में?
Always dependency.
False dependence. Like what is the false dependence? Vow and
Wow.
var. Is it? Because in false dependence, what you are doing basically is you are trying to write on some register. You are trying to write on some what? In raw मैंने गलत नहीं थी, पहले मैंने एग्जाम दी थी raw की, वो मत गलत ही थी, क्योंकि मुझे वहाँ a चाहिए था, जो मुझे a है यहाँ पे इस्तेमाल हो रहा है वो मुझे ज़रूरत है, लेकिन वैव एंड वॉर्ड में हम क्या करते हैं, किसी रजिस्टर को राइट कर रहे हैं, ठीक है, फिर मुझे इसी का चाहिए जो इसमें R1 में है, मैं R1 का नहीं चाहिए मुझे, मैं R1 में इसको डाल रहा हूँ फॉर एग्जाम्पल, R1 में फिफ्थ में R1 में कुछ डाला मैंने एक इंस्ट्रक्शन ने, अब दूसरे इंस्ट्रक्शन को भी R1 चाहिए होता है, R1 का वैल्यू नहीं, R1 रजिस्टर चाहिए होती है, जगह चाहिए होती है, तो मैं उसको रजिस्टर रिनेम करके मैं कहूँगा यार तो दूसरे रजिस्टर ले ले, कोई प्रॉब्लम नहीं है, ठीक है, लेकिन रा में जो R1 में है वही चाहिए होता है, जो R1 में है रजिस्टर में है वही चाहिए होता है, दैट मीन्स यू हैव नो ऑप्शन, यू हैव टू वेट, क्योंकि जो R1 में बनेगा तब जाके आप कर सकते हो, ठीक है, इट इज लाइक कि आपका दूध उबल रहा है, फिर चाय बनानी है, चाय के लिए दूध चाहिए, लेकिन अब आपको चावल बनानी है, चावल के लिए दूध नहीं चाहिए बल्कि वो पतीला चाहिए था या वो कंटेनर चाहिए था, हम कहते हैं तो वो कंटेनर मत ले, तो दूसरा कंटेनर ले, तो तेरा पंगा सॉल्व। लेकिन चाय के लिए प्रॉब्लम है, जब तक दूध नहीं आएगा आपको तो चाय नहीं बन सकती। अब आप ग्रीन टी के शौकीन हो, उसमें मैं कुछ कर नहीं सकता, मैं मिल्क वाला पीता हूँ, इसीलिए मेरे फैटी लिवर हो गया। यू गेटिंग व्हाट आई एम सेइंग? ओके, so why are you underestimating your college teacher? He has given you wonderful slides.
Slides तो अच्छी है लेकिन
It's recording. So we can do shelving, we can do register renaming, we can do speculative branch processing. So where we will be doing speculative shelving, you can't understand right now, because what I do is maybe tomorrow we'll discuss this, right? This is a long topic. But this called speculative branch processing. You should be telling me which problem will be mitigated by speculative branch processing. Control dependency, exactly. Is it? It's control dependency means, yeah. So you do what? You speculate the branch and process and all that. He's showing the pre-decode unit and all that, right? Okay. This is the diagram which I want. Now, issue policy. Issue. If we have the issue policy, now what? Basically, issue policy tells us what?
how to remove dependency.
What kind of things we have? What kind of dependency we have? We may have the false dependency. We may have the control dependency. We may have other things also, right? So depending on that, we have these things. Depending on that, we have what? The salah time is coming, miraculously. I have to remove. So can't leave the salah now. At least not by now, right? So when you're in a problem, you remember God more, right? So issue policy. But I'm not saying I'm in any problem, but let me see what kind of things happen. I don't know what you guys are telling me about 10 is higher. Big thing. Okay, you cope with what? Cope with
False data dependencies.
false data. Azhar, you tell me. Fast dependency. Two guys in it. False dependency. Which one? Bob and Bob. So either you do nothing or you do something. Right. Okay, you got no extra provision. Either you do no extra provision as you do nothing, or you do what?
Register rename.
Yeah. Register renaming. We already discussed that, right? So only thing is, hey, this register is needed by the next instruction. So I'm telling you, hey, get some new register. Why to be having only that register, right? So register renaming will help to remove the false dependencies. So if we have the now here in the second part, let me discuss about unresolved,
Control dependencies.
because register renaming will not mitigate the problem of,
Control.
so unresolved, yes.
Control depends.
So how are you gonna remove the control dependency? Either you do what? Either you do waiting, or you do what? Branch prediction, speculative. What does that mean? This means I'm saying if this, then this, else this. Okay? I'm saying I can't, if I don't do parallel, these instructions in parallel, I'm saying, hey, unless this truth value is not evaluated, I can't execute this or this. So do what? Do waiting. Make this wait, these instructions wait. Don't do these. Wait them unless this is being done. When this is being done, you are in a better position to say this or that, etc. Or you speculate the branch. You in advance like predict where I will go. You know in advance about this if statement, and you have better chances that it will go here. So in this speculative branch processing is a huge chapter itself, which in a nutshell I can say you are predicting that by this if I have a better chances to be here. So I can execute these two in parallel. I don't wait for its execution. Or if you don't have the speculative branch prediction, what do you do then? Then do waiting. Wait for this instruction to finish. When it finishes, go for the instruction. You getting me? And then we have the shelving. Shelving is, we will shell it tomorrow. We'll do the shelling of shelving tomorrow, right? And what else? What else?
Handling of issue
Handling of
blockage.
issue blockage.
Yes, handling of issue blockages. If we have blockages, because I told you, if we have now the, what is left out among these? Ra. Okay? Now there you have to block. I told you, I can say the star, I can say block in that. Now block it. Now if we are blocking, how to mitigate this problem of blocking? That will land here, right? And I guess this is the end of this segment. So, with some happiness, see you tomorrow. Okay? Somebody messaging me constantly, right? Okay, anyways. Ma salama.